You can take a photo of me. Yeah, it's beautiful.
I think it's wise when you S.
Oh, yeah, that is how I write S. Yes.
Yeah. Oh, okay.
Sorry, just Jonathan Wise. So Jonathan Wise is in University of Boulder, Colorado, and Sam is in Israel at the moment. Yes, Tel Aviv. So if we're very lucky, Sam will join us for the last episode of this seminar and give a talk. But this is yet to be entirely confirmed. Sorry, organisers, I'm working on it. So the motivating problem is about compactifying families of abelian varieties, or ultimately families of Jacobians. And so, well, roughly the story is that there's a certain kind of compactification or relative compactification that we'd like to work with. Unfortunately, it doesn't exist. And so I'll explain the thing that we'd love to have and explain an example as to where it doesn't exist, and then try and talk about how this logarithmic approach might help us a little bit. So the general picture would be something like this. So S is going to be a scheme, or a stack, or whatever, it doesn't matter too much. And U contained in S is some dense open. Maybe schematically dense, but again, this is sort of hand-waving general nonsense things. So really, e.g., S could be something like the affine line, or spec Z, or whatever. And U would be something like S minus the origin, or spec Z, 1 over n. They don't have to be one-dimensional. I mean, you could take some more interesting example, but this is the kind of, I mean, your S and U can be something rather simple. And then we have A over U, an abelian scheme. So a family of abelian varieties, if you like. So it comes with, well, it comes with a map to U, which is implicit in the notation. It also comes with a multiplication and an identity and an inverse, which I'm not going to explicitly name. And so, well, this is an abelian scheme over U, but we'd like to sort of extend it to some model over S. And what can we reasonably ask? So we want a relative compactification which we might write something like A bar over S. So this is bar as in compactified, not as an algebraic closure. Well, what do we want of this? Firstly, we want it to be a compactification of A. So we'd maybe not even such that, let's say, with an isomorphism from A bar times over X with U to A. So it is really a model of A. Well, this is easy. You can take A bar equals A. So this is not very exciting. Well, ideally we'd like A bar to S to be proper. I mean, otherwise it's not, like, that's what the word compactification means, right? That we want something to be proper. And we also really like this A bar S to be a group scheme. So if you relax, and it's really the combination of these two conditions which is what gives us all the trouble. If you relax either one of them, it's in general pretty easy to construct such an A bar. Like if you only want a group scheme, essentially due to Raynaud, this should almost always exist, but I should worry about whether S has to be Noetherian or locally Noetherian or something. But basically, if you only ask for a group scheme, that will exist in pretty great generality. If you only ask for properness, that will again exist by Nagata and this kind of thing. But when you ask for them both, you get lots of trouble. So yeah, so problem such and A bar does not exist in general. So just, I'm calling it a relative compactification because I'm asking for the map from A bar to S to be proper. But I mean, S itself does not have to be proper or projective or anything like that. So this A bar is not, in some sort of abstract sense, proper over Z or anything, but it's just a relative thing. But the problem is that this A bar doesn't exist. So let's do an example. So to make my life easier, I'm going to let K be a field of characteristic 0. And I'm going to have S So S is going to be the affine line, and I'm going to remove the origin, and I'm actually going to remove the point t equals 1 as well, just for convenience, because I'm going to write down an equation. You could also take, oh, I'm sorry, no, just 1 over t minus 1, or S is spec. I mean, you could localize it t or take a power series rings or whatever, and I want to look at the affine line locally around the origin. And then I'm going to take U to be S minus sort of t equals 0, which is just spec K t plus or minus 1, and then 1 over t. So now, here's my S, and here's, well, U, I'm deleting the origin from S. And I should give you also an abelian variety. To make life easier, I'll write down an elliptic curve, because it's by far the easiest way to write down abelian varieties. So let's do that. So I'm going to have, I'll maybe draw a picture here. So A is going to be contained in P2 over U, and it's going to be given by an equation y squared z equals, I'm going to write a space. It's one of these things where if you write the equation sort of correctly, it's a bit of a mess. X cubed plus x squared z minus t x squared z minus t z cubed. So this looks kind of terrible, but really what we're doing is y squared equals x plus 1 times x squared minus t. I mean, if you expand out and put in the have I made a mistake?
Should one of the x squared z to be an x z squared?
Oh yes, probably this one. Yeah. So this defines me, well, it currently defines me a relative curve inside a projective plane. I'm going to choose the section at infinity to be the 0 for my group law, and then there's going to be the standard way of turning this into an abelian variety, right? Well, you can do the 3 points on a line sum to 0, or you can do take the canonical isomorphism to its Jacobian via p goes to O of infinity minus p. So however you set this up, this A thing turns into an abelian scheme over U. So the discriminant of A, if I computed this correctly, is like 2 to the 6 times t minus 1 squared. The 2 I don't have to worry about because I'm in characteristic 0. The t minus 1 I also don't worry about because that doesn't happen in S. But the t equals 0 is sort of, that's like, well, that's t equals 0 is the difference between U and S. It's the pointer that I threw away. Okay, so if I draw myself a picture, I have, well, nice sort of, these are my genus 1 curves. So over U I have this nice smooth thing, and now what I'd like to do is I'd like to make, well, this is my A, I'd like to try to make an A bar. And I must, well, I should fail, otherwise it would not be a good example of what I'm trying to say. So, try to build a bar of an S. So there's sort of a natural first thing to do, which is to just say, well, this equation makes sense over S. And so I can just take the same equation and it'll cut out something in P2 over S. Same equation. And so what does this thing then look like? Well, away from t equals 0, it's a nice smooth thing, but over t equals 0, it looks something like this. So this is the fiber over t equals 0. It's a nodal cut, so it's not smooth. Well, this is proper because it's projective. So we've managed the first point, but it does not admit a group scheme structure. There are various ways to prove this. You can sort of write down the group law explicitly away from t equals 0 and try and extend it and see that it goes wrong. You can do this in Sage or even by hand if you're so inclined. But I cheated, or I made life much easier because I said K is a field of characteristic 0. So we have this theorem of Cartier that any group scheme over a field of characteristic 0 has to be smooth, or any locally finite type group scheme over a field of characteristic 0 has to be smooth, and this isn't. So
it's in any characteristic it has to be homogeneous, right?
Yes, also.
And so it clearly...
Yeah.
For your adjectives, are you always including flat?
Probably be a good idea. I don't think it's going to make. I don't think I've said anything false, but it's probably a good thing to do, isn't it?
Are group schemes going to be flat already?
No, I don't think there's some horrible. Yeah. Yeah. I mean, you could just like. I think you can just like stick in an extra point randomly. You could, if you had an A bar, you could like stick in some random other point and make it 2 torsion. I think. Yeah. So let's not do that. I mean, we could also, if we had a non-flat one, we could take the closure of the generic fiber, and it would probably be flat because you're over DVR. But in this special case. Okay. So I will. Yeah. So this is no group structure because this theorem says that, well, as Lenny said, it should be homogeneous, but also it should be smooth. And it's not. So it's clear that this particular attempt at making an A-bar does not work, but maybe we just made a bad choice. You could always try to choose a different A-bar, but it doesn't work. And so it's like if you look at the sort of theory of semi-stable reduction of curves, you can see that any proper flat, thank you, Robin, any proper flat model you take of this thing is going to like not be smooth. Like the special fiber here is not going to be smooth. So in fact, there does not exist a proper smooth model. So therefore, there does not exist a proper group scheme line. And so what are we going to do about this? The thing is, I mean, you could also ask, why do we care about this problem? Like, you know, these compactifications don't exist, we should just move on with our lives, make do with what does exist. And indeed, this is what people have done very successfully for the last, coming on 60 years. So there are certainly alternatives to trying to find a proper smooth model. There is this business with Neron models, which is started by Neron in 1965 and all this kind of thing. And for many purposes, these are adequate. But there are lots of nice, like if you did have one of these proper smooth models, there are so many lovely constructions you could make. Like basically anything you do for abelian schemes, you could just do for degenerating abelian schemes, like Fourier-Mackay transforms and all this stuff. You could just run for non-smooth things. This would have some really nice consequences. So I think the goal of this seminar, I think in sort of, so Neron came and told us, well, you should give up on properness and make do with something weaker, and that was nearly 60 years ago, and we've been happy with that since then, mostly. But the goal of this seminar is to say, no, let's really try for something proper and smooth, but let's just generalize the definition of scheme so that we can make it exist. So, well, I guess in general in algebraic geometry, if a thing doesn't exist, then you just enlarge your category. And so there's this sort of traditional thing where we have schemes fully faithful embedding into algebraic spaces, which also have a fully faithful embedding into algebraic stacks. Of course, you can just carry on if you want, but I'm not sure what you've very informatively put here. And so what we've done here is to say that you can't find an A-bar in the category of schemes. Actually, moving to the category of algebraic spaces will not help you at all, because any group's algebraic space locally of finite type over a Dedekind scheme is a scheme. So this doesn't make things any better. I don't actually have a proof that this doesn't help. I'd like to be able to say any smooth proper stack model of A can't have a group structure, but I don't actually have a proof of that. I've never seen anyone make progress with this. It would look very strange.
But there's also these, what they call root stack models of log schemes, right?
Yeah, it's true, but it's...
I don't know if that doesn't maybe not literally solve this, but...
Yeah, I don't think that's going to help. But, I mean, it's a good point. There are... So, yeah, maybe one can make something nice here, please do so. That would be really, really cool. I didn't manage to prove anything about non-existence here. I mean, here it's very cheap. Yeah, so such an A-bar doesn't exist. We also haven't included the word log, so the idea is that we're going to put log somewhere, and then it will help. That's the goal of the next for occurrences of the seminar. So Salvatore is going to tell us the definition of a log scheme, and I don't want to like jump the gun and do that now, but to explain where we're going to go, I want to tell you just a tiny bit about what the definition looks like. So, I'm sorry, Salvatore, this is going to look like really ugly, but you will make this all beautiful later. So a log scheme is roughly a scheme with a log structure, which would be it's a scheme together with a sheaf of monoids and a map. So if we have a scheme, we have a topological space with a sheaf of rings. This is a familiar thing. A log scheme is where you start with a scheme, and then you have another sheaf, but it's only a sheaf of monoids this time, and you have a map from the sheaf of monoids to the structure sheaf, and it satisfies some conditions. Also, you have the notion of a morphism of log schemes, and unsurprisingly, it has to respect this map of monoids. And so, like, it has to play nicely with the monoids. It's sort of like, as you would expect, and as you will see in the next hour. So in particular, if you have a log scheme, you can forget the sheaf of monoids and get a scheme. Sorry, if you have a log scheme, you can forget the sheaf of monoids and get a scheme. So we have a functor. So there is some category of log schemes, and there's a forgetful functor, which goes to the category of schemes. And so most classical things that you do in algebraic geometry, they have log versions. And people generally just put the word log in front, so you have like logital, log smooth, log flat, log symptomic, log, etc., etc. And some of these behave in a very uninteresting way. So for example, log proper is just proper again. So more precisely, so f, maybe I'll put some notation. If x is a log scheme, then I'm going to write an underlined x for the underlying scheme of x. This notation becomes unfortunate when you have compactifications, but it is fairly, well, it's standard, which is not a great excuse for using bad. I think it's reasonable notation. It's not a vector, that's for sure. I'm not sure what else I would underline. I teach all this first year in the algebra, right? So I underline my vectors. I won't do that today. So if you have a map of log schemes, you would say it's log proper if the underlying map of schemes is proper. The consequence is that no one ever talks about being log proper because it's just the same as being proper. So it goes. At least I don't think so. I mean, yeah. But e.g., you could have f from x to y is log smooth or logital. This definitely does not imply that it's smooth respectively at all. So, for example, an example of the example, any toric variety is log smooth. So we're working the category, we fix a ground field, we work in the category of toric varieties over that ground field. Once we've seen the definition of a log scheme, we'll see that any toric variety naturally comes with a log structure. So every toric variety is naturally a log scheme over the point with trivial log structure, and they're all log smooth. But toric varieties are very far from being classically smooth. So this is a huge class of things which are log smooth but not smooth. And in some sense, this class is almost enough. At the risk of saying something false, like if I take anything which is log smooth, then I think étale locally, under some mild hypotheses that I forget, it will actually be a toric variety. Yeah, I know this is not actually true, but it's close to being true. I'm sorry. He's giving me nasty looks. He'll have to give a later talk and tell you the true versions. So this was log smooth. What about log étale? Well, toric blowups are log étale. again, this isn't an entirely precise statement because I haven't told you what the log structures are. You have to put the right log structure on the thing you start with, and then there's a correct interpretation of toric or log blowups, and then you have to put the right log structure upstairs. So this is all very hand-wavy and will, I think, become more precise later in the seminar.
But is the underline of a toric blow-up actually a blow-up?
Yes. So it's literally just like take some, like blow up the origin of the affine plane. With suitable choice of log structure, this is an étale map, or a log étale map. It's not classically flat, so this is pretty weird. Yeah, so we can do these things. Yeah. So this was my brief overview of log geometry. There will be more to follow. What do I want to do next? Yeah. So skip the page here because I had too many definitions on. So the idea is that we have this category of log schemes, and we'd like to use this to construct this. We want this A bar thing to exist in the category of log schemes. But this cannot work. And the reason is because essentially the functor goes the wrong way. When we're looking at algebraic spaces and stacks, they make the category of schemes bigger. But here we have a functor from log schemes to schemes. So if you built me an A bar in the category of log schemes, well, the notion of proper is the same as it was before. Flatness is not going to make any difference. We're a Verdelican scheme. And the group structure, if we had a group structure here, we'd get a group structure here. So if you made me an A bar in this category, I could just forget the log structure and get me an A bar here. But we've already argued that this doesn't exist. So just working with log schemes is not going to give us the A bar that we want. So the existence of this map, this functor, tells us that A bar can't exist.
Sorry, did you say that this forgetful map sends group objects to group objects? Or?
Right, so because if you just think of group in the most naive sense of like with a multiplication map and with an...
Sure, but I don't know if it commutes with products and all these things.
That's a good... So in general it doesn't, but it depends on whether you work... If you work in just the category of all log schemes, it does, right? If you work in the category of saturated, you have a problem. In the category of all log schemes, it does. That's a very good point, yes. Yeah. So, but no, that's true. In the category of saturated log schemes, then this function doesn't commute with fiber products. And then you're right. Then there's something still to be checked. So that's a really good point. And so we need something more than log schemes. And so for this, there's this notion which appears in, Molko and Wise don't actually talk about these things, but they appear implicitly in their paper, and Carter really talks about these things. So maybe that would be useful to do, which are these log algebraic spaces. So here we have, make myself a little bit of space, so we said we had log schemes here. But it turns out that there's bigger things. And so these things will sit inside log algebraic spaces, and now this is where it gets like unpleasant. There's actually two notions of log algebraic space. One of them is sort of simple and comes with a forgetful functor down here, and so it won't help us. There's also a weird notion of log algebraic space, and that genuinely makes the category bigger, and that's what we'll work with. So I'll present you with the sort of interesting notion of log algebraic space, and that's exactly what our A bar will exist as. So let's recall. So an algebraic space. Is roughly a functor from schemes to set, admitting an étale cover by a scheme. So I better require that my functor is a sheaf for the étale topology, and there's also some conditions on the diagonal which depend slightly on which reference you're using. But the important thing is that it's some nice functor which has an étale covered by a scheme. And so we can make a log version in a sort of very natural way just by putting the word log in a bunch of places in this definition. Maybe this would be, this is a moment for the colored chalk. So wherever we see a word which could have a log in front of it, we insert the log, and then we have a new definition. Again, we have to be careful about the diagonal, and in the paper of Malcolm and Wise, they do check relevant conditions on the diagonal.
The log sets.
Fortunately not.
The log functor too.
And so most of this is like not very surprising. Like, okay, it's now called a log algebraic space. It is a functor from log schemes, and it's covered by a log scheme. But really, the important thing is this word here, this log ital cover, because as we've seen, log ital is very, very different from classical ital. So this is and so, in particular, there's no reason, and it is not true, that if I have a log algebraic space, that it has an underlying algebraic space. So any log scheme has an underlying scheme. This is fine. There's this forgetful functor. But there is no forgetful functor from log algebraic spaces to algebraic spaces. They genuinely make the world bigger.
But then what does the word cover mean?
So it means universally surjective. Like, so it's a log ital. Sorry, what's the?
I mean, because surjective, then I think I take the forgetful map and then I check.
No, so you mean, so right, that's a really good point. So it means universally surjective in the categorical sense, and this is not equivalent to surjective on points.
I guess it could mean like subjective as sheaves, right?
Yes. Yeah, but sorry, that's what, like, yeah. It's surjective as sheaves, but that's not equivalent to surjective as sets, unlike in usual algebraic geometry. Yeah, that's something which we will enjoy meeting later on.
So David, just a comment. Before you wrote log everywhere,
Yep.
I was kind of okay because I know what a tile map of schemes is, but I also know what a tile map of functors is, because
Yes.
I have to mirror in order to interpret that.
Yes. What's an ital map of functors in this? What's a log ital map of functors?
So yeah, I guess log ital can also be characterized in terms of functors, not just the.
Yes, that's a really good point. It can be, so you could, and it's very similar to the case of schemes. You have to characterize like local finite presentation as preserving limits and colimits, and you have to characterize, you have an infinitesimal lifting property, and you take the usual diagrams, and again you put the word log in as many places as you can imagine. That's a very good point. One does have to think long and hard about these things, and in the end it does all work out. In my memory of Cato is that this is sort of left as an exercise to the reader, which I somewhat failed to do. But then I asked Jonathan, and he told me how to do it. So. Okay. Yeah. So by the end of the fourth occurrence of this seminar, we will have constructed, at least in the case where, so we will not do this for general abelian schemes, but for Jacobians, we will construct a thing which sort of is this A bar, has it's going to be log smooth and have a group structure and be proper. There is also a notion of properness in this context. And it's going to be one of these log algebraic spaces. So this A bar exists with all the conditions you could want in this category of log algebraic spaces. And that's really that's sort of the ending point for the paper of Malcolm and Wise. But in some sense, if this is where the story stops, it's quite unsatisfying. Because, okay, we've constructed this thing in some really quite unpleasant category, and what is it good for? We had all these dreams of things, if it was a scheme, then we have all these dreams of things that we could do, but it's not a scheme, and there's no underlying scheme, there's no underlying algebraic space or anything. And this is work in progress by the same authors, so they now have in the Jacobian case, they have a theory of principal polarizations on Jacobians. They have some nice delinear pairing on well, I guess that's the same thing when you pull back the Poincare bundle on the A cross A dual, and they have Picard-Lestrade formulas. A lot of the things that you would classically want do actually work in this context. And this, unfortunately, goes beyond what we'll treat in this seminar, partly for reasons of time and partly because it's not published yet, or not on the archive yet. But this is sort of a promise that, well, what can I say? This is as far as I'm aware, or as far as I expect, this is actually a sort of a good thing to do. this classical constructions which make abelian varieties actually useful, like having these polarizations and things, really go through even in this very strange category. So that is the end of the first, just over half of the talk. So my plan for the next part is to talk about much more classical things, about the classical Picard functor. So maybe, are there any questions about this first bit?
Yes. You seem to stress that the map goes the wrong way, from log schemes to schemes and other way around. But to make sense of your definition of a model, you need a map the other way around, because over you need to compare it with a given thing.
Yes, so there is a map the other way, which is called the take the trivial log structure map.
And it's a left adjoint to the forgetful map, or is it?
I think so. I'm not sure.
It's good. Yeah, joined in one direction.
Yeah, but
I mean, is it like a free object, or is it like a... we'll see this.
This is a very good question, which yeah. I mean, so what do you, yes, that's a very good question. I'm not sure what the answer is. I mean, the answer is we take the trivial log structure on A over U.
Yeah.
Nothing surprising happens. Yes. Any other questions? Easier ones are welcome. Okay. So this has been this is the log bit, and hopefully it will make a lot more sense when we've actually seen the definition of a log scheme and things. It will probably help a bit. But I wanted to try to give an overview of where we're trying to go with these things and why we have to work with these rather odd objects.
Taking the trivial log structure as a left adjoint.
Thank you. So the next thing I want to talk about is the classical Picard functor. No logs anywhere in sight for the rest of this hour. The references for this, there's the book, Narrow Models, of Bosch, Lukagomet, and Reynaud. And there's also this FGA Explained. And this is the last chapter, I think is due to Kleiman, if anyone, yeah.
Yes.
Yeah.
Probably FGA Explained is just the better reference for the purposes of what I'm doing today. But the Narrow Models book is very complete. So I'm going to start in a sort of a. Am I going to start in a similar way? It doesn't really matter how I start. No, I don't know why I started. I started with this S and this U business, but I don't know why. I think S is fine. I see no need for a U. Okay. Grand. So S is a scheme, and F from X to S is a separated morphism of finite type. But really, oh no, this is actually going to cause me trouble because I'm going to switch about halfway through to the case of curves, and I'm going to forget to tell you, and then I'm going to confuse you. So I'm going to call it C, and I'm going to let it be a proper flat curve, and this means the geometric fibers are reduced, connected, dimension 1, and all non-smooth points are nodes, ordinary double points. So this is the setting which we'll be working in later in the seminar. The things I'm going to say will initially work in much greater generality, but then in order that I don't forget to introduce my assumptions, I'm going to restrict now to this case. And so what we'll see in the second talk of the next edition of the seminar is that such an object admits a log structure. It actually admits many log structures, and it has a sort of universal or minimal log structure. But in this part of the talk, I promised no logs, so I guess I lied. There will be no more logs. And so we have this naive. Doesn't look good.
No.
Is that better?
Yeah.
A bit. naive relative Picard functor. It's just occurred to me that I have an entire other blackboard that I have not yet used. Sorry. Well, I will try to remember. The next time I start erasing, please shout at me, and I will try to do better. So this is called pic C over S, which goes from schemes over S. So I always put these ops because I don't like contravariant functors, but so my functors are always covariant, but if you are happy with contravariant thing, you can erase the ops, it doesn't matter. So this goes to the category of abelian groups, and what am I going to do? I'm going to send T will go to pic of X. T pic
C.
Thank you. It begins. That's the problem I get with this chain. So I should say what these things mean. So general pic of anything, which I could call X, that's good, is just the set or the abelian group of line bundles on X. Modulo isomorphism. Equivalently, GM torses on up to isomorphism. Maybe I don't want to say this because there's an issue of whether I insist my torses are representable. I think I'm fine in the situation, but I should not improvise things that I can't remember the details of. I wrote AB for abelian groups, so the group structure is tensoring together, so this is not so surprising. What is this quotient thing? Well, if I have a line bundle, like I have CT mapping down to T, this is C plus S with T, that's good notation to recall. If I have a line bundle here, I can pull it back to a line bundle on CT, and I'm just going to divide out by these things. For people who don't like dividing out by isomorphisms, that's great. There's also a version where you don't divide it by the isomorphisms, and then it's called the Picard stack. And actually it's in many ways easier, but it has the downside of being a stack, which makes it less easy sometimes. So, well, we have a Picard functor. Why is it called the naive Picard functor? I think the naive, there should be an accent on the I. I'm quite sure. The right kind of, no, not sure. Why is it called the naive Picard functor? Because the naive relative Picard functor is because it's kind of not very good. The problem is that it's not representable in general. So this C over S is not representable. In general. And worse, it's not even a sheaf. E.g. with a risky or eternal topology. So here I mean sheaf in the sense of quotient topologies, so I can view this as I can put this risky topology on this thing, so I have the big site over S in one of these topologies, and then if the functor was going to be representable, it would in particular have to be a sheaf. And this isn't. So there's sort of a very traditional example of this problem, which I shall repeat. So the traditional case is to take where C to S is a conic without a section. And why did you do? And S prime to S is a cover after which C does have a section. Well, C S prime does have a section. So, I mean, when I say cover, I mean whichever topology you care about, it should be a cover in that topology. So the example of the example. We could take something like S as spec Q, C to be given by x squared plus y squared plus z squared equals 0, and then S prime is spec Q adjoint I or something like that. So this is a Natal, but not. This is a Natal version. You can certainly make more general versions or less general versions. quite low down for you guys, right? Yeah. Maybe I'll just fit a like here for you again.
Might have to be
A bit lower.
quite a bit.
Yeah. To not adjust this at all now. What do I say? Right. Okay. And so maybe we should give this section a name. Sigma. I always call my section sigma. I don't know. Sigma for section. Yes. And so we have this O. So C to S, C S prime to S prime is a relative curve, and so the image of this section is this section is a closed immersion, and the image of the section is a divisor, a Cartier divisor, because the curve is smooth. I guess conic implicitly meant to say smooth. And so O of sigma is a line bundle on here. And the silly thing is that, so this gives us a point in, so the class of this thing is a point in hic C over S of S prime. But the silly thing is that it's a Galois invariant point. So if I hit this with the, well, I guess I'm now looking at my example of Q join I over Q. If I hit this thing with like the complex conjugation, then it gives me certainly a different section, but the problem is that this is a conic, a genus zero curve, and so these line bundles will be isomorphic. And so this point in this Picard scheme is actually Galois invariant, and so if this was a sheaf, it would descend to an S point, but it doesn't. Basically because there is no, I just said there is no section, so you will not have an effective, you don't have a line bundle degree 1 which has a global section. So this is a Galois invariant point. That does not descend to or come from S point. And so the classical approach to this is to say, well, it's not a sheaf, so let us sheafify it, and that will fix everything. And indeed that works. The other approach, which is maybe the other alternative approach is to say, well, the whole problem comes because you divide that by the isomorphisms. Like, this thing morally shouldn't be Galois invariant, it's just sort of an unhappy coincidence that when I hit it with the Galois action, because the Picard loop of this thing is trivial, then it happens to be the same point again. So if you just work with a Picard stack, then this example goes away and you really get something representable. But if you really want to scheme, sorry, I mean you have to prove, like, that's not a proof. But if you work with a stack, you get something which is algebraic.
So the problem being that there is no canonical isomorphism between the, when you work with the stack, you still have the issue, of course.
Yes.
That you described, but there is. It's not so much about dividing out isomorphisms or not dividing out isomorphisms,
okay,
but about
a canonical choice
yeah.
of yes. Okay. Yeah. And indeed, there's no right. So from O of sigma to O of conjugate of sigma, there is lots of isomorphisms, but no distinguished one, which is there. Yeah. Thank you. Okay. So to solve this, we just sheafify it. The function. But now you have a sort of an awkward point, which is what topology do I want to sheafify it with respect to? I could sheafify it with respect to Zariski et al., FPP, FPQC, anything I want. And a priori, these will all give me different answers. Maybe some will randomly representable, some won't. It could be a complete nightmare. But actually, things are much better than that because I'm working, now I'm really happy that I'm working with a nodal curve because this thing has sections et al. Locally on S. And so it turns out that if I sheafify with respect to the et al. Topology, then the resulting thing will be representable. And moreover, if I sheafify with respect to any finite topology, I get the same answer, which would still be representable. So there isn't actually so much to worry about. So we have a theorem, which is in, for example, in FGA explained, which says that, some notation before the theorem, so the theorem makes sense. So so if tau is in Zariski tau PPF PQC. I'm going to write pic C over S, what's my notation, comma tau for the sheafification of the naive one in the topology. And so now I've done the terrible thing of making lots and lots of these, but the theorem will collapse most of them back together again. So the theorem says that pic C over S comma et al. Is the same canonically as pic C over S comma FBDF. So another way to say it is that when you've sheafified it with respect to the Étale topology, it's automatically a sheaf with respect to all the other ones. And is now let's go over here and is representable by a smooth algebraic space over S. And so the reason it's smooth is because if you look at the deformation theory, the obstructions live in H2, but we're working with curves, and so the H2 vanishes for silly reasons. So it certainly gives you something smooth. If you're not happy with an algebraic space and you'd like a scheme, then you can arrange that by putting some sort of mild assumptions. If you replace proper up there with one of the notions of projective, at least, then what you get here will actually be a scheme. So this, in the end, is sort of a non-scary gadget. Okay, and what on earth does this have? What else am I supposed to say? Yeah. So we started with this. This is the last thing to say, maybe.
Are you sure it's not always a scheme in your context?
I'm pretty sure. I mean, but I would have to. I mean, like, I'm not 100. I may have misremembered something. There is. I mean, there's this example of Mumford in this. I know where I would look for the example that I have in mind.
And it's an example with a curve.
An example with
Okay.
a curve. Yeah. But it's also possible that I've misremembered something. Like that can happen. But I think that it's really. So the fiber-wise connected component of identity, because this is a group scheme, so it has a fiber, that is always a scheme.
Ah, okay. Then
Maybe that's
what. Yeah, sure.
If you're working over a Dedekind base, it's a scheme. So there are lots of cases when it's a scheme, but in general, I think not. So given some integer d, we can write pic d c over s. So now I have a notation issue. I don't really want to. Okay, so I can write the act. I'm not going to write this so many more times for the sort of subfunctor where the line one is degree 0. Sorry, degree d. With bad notation otherwise. Every fiber. Well, this is a bit imprecise because the fibers could be not irreducible, so let's say total degree. So in other words, if I have a fiber, so if I have like 7 here and minus 5 here, then the total degree is 2. So I'm not going to distinguish these. I'm just going to like mash all of these together. So this is degree 2. So this is a subfunctor. Actually, it's not only representable, it's an open and closed subfunctor. So it's sort of as nice as you can be. You can cut this Picard algebraic space into connected, relative connected components. True. No. So these don't have to be connected. you can cut it up into pieces. So these are open and closed. And if C over S is smooth, then pick 0 C over S is an abelian scheme. And this, I mean, proving the properness of this is actually easy, right? Because you just have to check the value of criteria. Well, you have to check some quasi-compactness, and then, which is actually the tricky bit, and then the value of criterion should be okay. Ooh, but let me not try and do this off the top of my head with 4 minutes left in the talk. That would be kind of silly. And so, so this is some abelian scheme, and so the idea is that we start off with our. So in the beginning of the talk, we had an abelian scheme, mapping down to U, which was open